Okay, and wishing Christian and Nitty well. We're sorry you guys couldn't be with us. You can see we've got a couple of learning targets. I can apply the fundamental theorem for line integrals. Wow, there's a fundamental theorem. We're going to talk about that in a moment. And then I can determine if capital F, which would represent the vector field function, if it's conservative. And by the way, if your vector field is conservative, that's truthfully the best news that you could hear about. It will make your life so much simpler in regards to working out some of these integrals. Let's take a look at what's going on, though. Last year, we extensively used the fundamental theorem of calculus. That showed up so very much. We had f prime of x inside of our integral. We took an antiderivative and we evaluated that, plugging in our upper bound minus our lower bound. We're not going to prove this today. The proof is a little bit tough here, but if you think of the gradient vector f of a function as a sort of derivative of f, then the following theorem can be used as the fundamental theorem. So let's say that we were integrating a line integral, but normally you can see that we had capital F inside of there. If capital F, that function, that vector function that would represent the forces, if it's really a gradient, amazingly, we could say, well, take an antiderivative. You'd have the original function f, plugging in r of b. Remember, we'd have a vector function really defined parametrically, and we'd say plug in our end t value minus plugging in r of a into that. So amazingly, you'd be able to work out this line integral simply and easily. Here's what we're talking about. In 2 dimensions, perhaps you're going from one point to another, x1, y1, all the way up to x2, y2. And let's just say that we've got the gradient of f here, and the gradient of f is typically been represented as a capital F. Little f itself is something else, so that when you take the derivative, partial derivatives of x and y, you'd get that vector function. But whatever that f is, I'd plug in f of x sub 2, y sub 2 minus f of x sub 1, y sub 1. In 3D, it's pretty much the exact same thing. You'd have a beginning point, you'd have an ending point. And we'd say, well, look, if you have a gradient function inside of your line integral here, that means that the gradient, like we said, was a sort of derivative of a function. F would be the function that you're taking the derivative of. Well, as we take this antiderivative, we just have f of our ending point minus f of our beginning point. And again, the gradient of f, what we're seeing here, is it was a type of derivative. It was all a partial derivative vector function. The I component was the partial derivative of f with respect to x. The middle component here, the j component, was the partial derivative of f with respect to y. The k component was the partial derivative of f with respect to z. Wow, if you know what that function is that you were taking the derivatives of, you could really just jump to the end of the problem and work that out. In either of these cases, whether you're in 2D or 3D, these integrals represent the net change in f from an initial point to a terminal point. So a little while back, right at the start of our unit here, we were looking at a force field, a vector field, the gravitational field that is so very famous in physics, and really that's Newton's law right there. So as you're moving a point from a starting point at 3, 4, 12 to 2, 2, 0, you might wonder, if we could perhaps work this thing out. Remember, we said that the force field, this vector field, was a conservative vector field, meaning that capital F was the gradient of F, and F, if you remember, the function that we were taking partial derivatives of was mg all over x squared plus y squared plus z squared inside of a square root. So, of course, as we would work this thing out, you could say, could we evaluate the work done? And in essence, what's happening is you've got this gradient function, which is really capital F, and we could say dot dr, and we're trying to, work this thing out, and we're going from a T1 to a T2, and you might not even know what those T's are. But what we're really saying is, hey, if you know this is a conservative vector field here, if you know that capital F is the gradient of some little function f, then what you can do is say this is f of your ending point minus f of your beginning point. Notice what we're really saying here. We're not needing to do a parametrization. We're not requiring us to even work out an integral in regard to what we were doing for so many of these problems. What we're saying is, hey, work out f of 2 comma 2 comma 0 with f of where we started, 3, 4, 12. So let's do that. Let's work this thing out. We'll say this is m, capital MG. And again, I'm just coming right back up here. We'll say it's the square root of our x squared plus y squared plus z squared minus, well, we'll have MMG. We're going to plug in our beginning point, which was 3, 4, 12. Down here, we'd have 3 squared plus 4 squared plus 12 squared. Guys, you work this out, you've evaluated your line integral. Wow, that's cool. Look, 2 squared plus 2 squared, I think we could, in a heartbeat, know that 4 plus 4 is going to be an 8, and radical 8, of course, is just going to be 2 root 2. So, if we were to clean this up a little bit, we'd have MMG all over a 2 root 2. And then over here, we'd have M, capital MG. Down below, 3 squared plus 4 squared. Isn't 3 squared plus 4 squared really 5 squared? Would you agree with that? Wow, and then you'd say, well, then I've got 5 squared plus 12 squared. Wait a minute, that's 13 squared, isn't it? Oh my gosh, wow. That bottom denominator is just a 13 right there. So, wow, we could factor out an MMG and, really, just go ahead and work that thing out. I'm even going to say et cetera, cleaning that up. I'm trying to be good with our video. But you get the point. If you have a conservative vector field, and if you know what that function f is that you've taken the gradient of, you can work some problems out lightning fast. That's really cool. By the way, could you have still worked them out the way you've done last week? You bet you get the same answer, right? That's the cool thing. Well, look, one of the things that we pointed out last week was that, the path connecting 2 points could very definitely yield some different line integral values. We took a look at connecting 2 points with a segment, connecting 2 points with a parabola, and we saw that we got some different answers. Even the other day, we reversed direction, and we didn't get the same answer. We got the opposite of an answer, didn't we? But here's what's going on. If you have the same beginning points and the ending points, what we're really seeing is, according to this, if F is, capital F, is representing a conservative vector field, that means that we'd have the same gradients inside of our integral, and then we'd just say f of our ending point minus f of our initial point or beginning point. What this is really saying is mind-blowing. You're saying that now you should get the same answer. This is called independence of path. When you have a conservative vector field, that is, again, what's a conservative vector field? That's when capital F is equal to the gradient of some function here. If that's true, it doesn't matter what path you go from a starting point to an ending point. No matter which path you go, you get the same line integral. Unbelievable. Wow. And that would definitely hold true if you think about it, if the fundamental theorem of line integrals is true, and of course it is. Here's yet one more mind-blowing application. Let's say that one of the curves you're looking at is closed. In other words, you start at this point, and then you end at the same point. Well, wow, if you realize that, then wouldn't you be plugging in the same point at the beginning and at the end to your function? And then f minus that point minus f of the same point should equal 0. So if you have that independence of path, that's really implying that your line integral would be 0 for every closed path. So how could you apply that? Well, in physics and in other sciences, you could see that, trying to make sense of it, the work done, remember we've been calculating work, the work done by a conservative force field, like a gravitational field, or like you'd see an electrical field has that same inverse square law relationship. If you had one of those, as it moves an object around a closed path, that work is 0. Wow. Well, just continuing a little bit, this theorem right here, it's saying suppose that you have a vector field F and it's continuous on an open connected region. And if you've got independence of path, then F is a conservative vector field. That is, there is this relationship. Here's the problem. Even though this is true, imagine how hard it is to show independence of path. To show independence of path, you'd have to say, think of any two curves that have the same beginning and ending points, and you'd show that you'd always get the same line integral. You'd get the same integral value. That's really hard to show. It's a true theorem, but it's not really useful to us at this point. Let's say that we've got a connected region. In other words, it's not going to have a separated domain. You're not going to say that your x values are okay over here, but then you're not allowed to use x values for a little while. They're undefined, make your function undefined, but then they're okay over here. So you're not going to have a disconnected, a not connected region. Let's just say it's all connected, and that means you can join any path in there. Let's say that you have that to be true. If you have independence of path, then F is a conservative vector field. Again, it's the same frustrating situation. You could say, my goodness, we need something a little bit more practical. It's this major question right here. How is it possible to determine whether a vector field is conservative? Because if it is, we can use that really cool shortcut, right? So we want to know, how can we say that I now know that vector field here is really the gradient of some other function. So suppose that we have our vector field, and suppose it is conservative. Now that seems to be the wrong direction, but that's okay. We could say that if that's the case, then we know that by Clairaut's theorem, we could say that P was really going to be the derivative of F with respect to X. Remember, that's what the gradient of F is. It's, this derivative of F with respect to X. and your y component would be the derivative of f with respect to y, we're going to say by